Cool.
All right, we're good?
Yeah.
Cool. All right. Well, welcome everybody to your final lecture of CS 205A. Congratulations, you've made it this far, and now you just have somewhere between 0 and 2 homeworks to complete and a final exam, and you're out of here. So is it we're good? Cool. Right. So a couple announcements. So just in case I have too much to say and have to end the lecture early. For one thing, homework 7 was due 2 days ago. If you haven't turned it in, you've got, what, 3 more days before you get it, before your late days start kicking in, if you've managed to accumulate them this long. And then you have this optional homework 8, which is due a week from, well, it's due this coming Monday, on the 9th. This Friday, the TAs will be leading a final exam review. And your final exam is on the 12th. Once again, your final exam is not in this classroom, okay? If there's one thing you can get out of CS 205A this quarter, it is that your final exam is not in this classroom. It's in Gates B3. If you go to this classroom, there won't be exam papers, there won't be me or your TAs, and you wouldn't want that. So go to Gates B3, December 12th. Remember, there were a couple people that asked me if there could be an alternative final exam time, and I told you to email me during the last week of class to remind me, even if you've already asked. I have received no emails. So, unless I hear otherwise by the end of the week, we're not going to have an alternative exam. All right? Is that a good threat? I don't know. But yeah. So if you can't make the final exam, it is your responsibility to ensure 100% and confirm with me and the TAs that you have some alternative time to take it. Yeah, cool. Are there any procedural questions before? We'll kind of wrap up at the end of the lecture a little bit. But is there anything, Martina?
So do we get 2 pages of notes?
Oh.
Or 1 page of notes?
Yes, your final exam. It is cumulative. It covers the entire breadth of CS 205A from day 1 to day whatever this is, 70-ish. It'll be very similar to the midterm in format. Like you'll have some number of questions. You'll probably let you skip one, maybe there'll be an extra credit question for fun. And yeah, and I'll let you have 2 sheets of notes in case you want to just reuse your midterm sheet, that's fine, and then just add a second sheet for whatever happens past the midterm. Cool? Probably the length of this exam will not be that much longer than the length of your midterm, although you'll have 3 hours instead of 1. Given performance on the midterm, I think that's sort of an appropriate choice. Any other procedural things? Once, twice? Cool. All right. So, a couple things. Once again, I'm supposed to remind you that your course reviews are to be submitted on Access. Once again, your input is very valuable, both for my teaching as well as for the future of CS 205A, which is likely not going to be for my teaching. And so, please provide your input online. If the sort of out-of-the-box questions that they, or rather inside-of-the-box questions that they ask you on the online review page are insufficient for the hopefully delightful things that you have to say, please feel free to email me. Or, I don't know, I suppose you can email the department if you're super unhappy with this class or something. But I hope that's not the case and that you've talked to me before. Yeah, so that's that. Once again, the course notes are going to be prepared into a textbook, hopefully, and your help is very much requested. If you're interested in doing this in the next 2 quarters, let me know. I've already gotten a couple emails from students that want independent study units to kind of go back through, implement some of these methods, and so on. Cool. All right. So unfortunately, the last lecture, we still do have some technical content to do. It's not all just information about your final. Right, so if you'll recall, this week is all about partial differential equations. Right? And unfortunately, PDE is kind of a weird topic to cover in this class because you guys don't have all the prereqs that you need. So our goal this week is to kind of go over some examples of PDE that are more or less kind of reasonable equations that you might solve, highlight some important aspects of the theory, and then go through sort of key examples of how you might discretize different partial differential equations and solve them. So at the end of this lecture, we'll actually go through 2 examples from, I think one from image processing and one from sort of computer graphics, CFD, and go in a little bit more detail how some of this machinery is actually used in practice. Cool. So, right. So, if you recall, a partial differential equation is nothing more than a differential equation that couples different relationships between derivatives. right? We talked about a lot of examples of this, things like fluid simulation, where the gradient of the pressure can affect how the pressure moves over time, or how fluids move over time. This makes a lot of sense, right? Because a fluid probably wants to move from a high pressure area to a low pressure area. And so that's a spatial relationship that's affecting how things are changing in time. So you've coupled two different derivatives. Yeah? It's pretty reasonable. In addition, we'll see later in lecture a concrete example of where you might have an image operator, right? And you can formulate a lot of image problems as PDEs. And oftentimes, images have X and Y axes, right? When you take a photograph, it has 2 dimensions. And you want to couple the behavior of your filter in these two directions. Yeah, so it's very reasonable why you might want to solve PDE in practice, and indeed there's a lot of machinery to do that. Now of course, as we talked about last class, you have to be a little bit careful when you formulate a PDE, because checking that a solution even exists, either globally or locally, can be quite a challenge. And there are a lot of cases, for example, even the Navier-Stokes equations, right, the world's most famous equations for fluid, that we don't know if there's a solution or not, right? We suspect there is, and our discretizations of these things seem to give us reasonable output, but we don't know this for sure. So anyway, you have to do your homework when you do PDE, both empirically and theoretically, to make sure that your software is going to work. Yeah? Oops. Right, so to continue in our little 5 minutes of review here, oftentimes a partial differential equation comes with boundary condition, and so we call PDEs boundary value problems, right? So for example, this little example of variational calculus that we did last lecture, where you had a domain, right, omega, and somebody gave us the values of a function on the exterior of the domain. Remember this one? And our goal was to take the values of the function around this border and interpolate them into the interior in a smooth way. Yeah? And what ended up happening was you had 2 different ways to solve this problem. You could either minimize an energy that took, as input a function from the whole domain omega and gave back, for each point of omega assigns a number to it. And we wrote down an energy function E of f that kind of looked like the smoothness. I'm not going to bother going back through all this. Yeah? And so you could either minimize this energy function over all possible functions f, which kind of looks like the story that we've had before in this class, although the difference is that our input is a function instead of a number or a point in space. Yeah? Or we showed that this is the same as actually solving a partial differential equation, which was Laplace's equation, grad squared f equals 0. Yeah? And so there's this duality here, which is, again, even though the math of going from here to here was a little different, and you saw I screwed it up a little bit on the board, but nothing major, the story is exactly the same as in previous parts of this class, right? I took an energy I wanted to minimize, I took something that kind of looked like its derivative, and what came out was effectively a system of equations. Yeah, it's exactly the same as what we've already been doing in this class. Right, so why do we call this a boundary value problem? Well, it's pretty obvious. We know the values of f on the boundary. We call the boundary, remember, partial omega. And our job is to fill it into the interior using this relationship. Yeah? And we have 3 different types of boundary value problems. Dirichlet problems, which is what I sketched for you here, right, where I just prescribe values on the outside. Neumann problems, where I prescribe the derivative of your function on the boundary. So for example, maybe I'm doing some kind of heat diffusion, and what I care about is the flux of the heat out of my domain. Yeah? Or in some cases, although we haven't really motivated these a whole lot in Tool 5a, you might want mixed or Robin conditions which combine the value and the derivative on the boundary. Sort of generalize these 2 cases. Cool? All right. So from there, we define this model equation. And if first order isn't enough for PDE, we need a second order model equation. You'll see that conveniently I fixed the typo from last lecture's slide here. And the model equation is nothing more than the all possible linear ways to combine the second, first, and 0th derivatives of f to couple them in a nice way. Right? And your job is to solve this equation for f. Yeah? And we introduce this gradient operator. Remember, the gradient, at least in 3 space, the gradient kind of looks like d over dx, d over dy. It's kind of a notational convenience. Easy, yeah? And this gradient operator allows us to express the model equation in a very slick way. And then the other thing that we notice is that, well, this funny expression in terms of the gradient operator looks an awful lot like the energy that we wanted to minimize when we were talking about gradient descent, or yeah, gradient descent and conjugate gradients. Remember this? We had conjugate gradients and gradient descent we wanted to minimize. I mentioned this on Monday too, right? 1/2 x transpose ax minus b transpose x. Right? And the minimum of this tells ax equals b. Similarly here, you have a nice looking quadratic form. And in fact, the behavior of this matrix A is going to determine how our PDE kind of looks. The same way that whether this matrix A was positive definite or not determined whether we could use conjugate gradients. I'm trying to emphasize with you guys, because we don't have that much time to talk about PDE, the commonalities with the theory that we've already seen in this class. Okay. So finally, for an itty bitty bit more review, what we did then is we said, okay, we have this model equation, and in fact, we classify the PDE based on the highest order term, which is the symmetric matrix A. Yeah? And in particular, you can check whether it's positive definite, positive semi-definite, whether it's got one eigenvalue whose sign is different from all the rest, or in the worst possible case, the matrix is just a hot mess and there's nothing we can do with it. And at least in the first three cases, there are some very well-established techniques for discretizing these PDEs. The fourth one, this ultra-hyperbolic case, is a very advanced one. And I encourage you to read about it online, but we won't cover it in this class. Right. So, finally, we ended class on Monday by sort of making an analogy between derivatives and functions versus matrices and vectors. Right? And we said, well, a derivative acts on a set of functions in a linear way, just like a matrix acts on a set of vectors in a linear way. You see, I'm going to keep pushing this analogy to linear algebra. You know? And in particular, in fact, we found that when we tried to discretize differential operators, what we ended up with was actually just a matrix multiply. Yeah? So for example, the matrix here, what we said is, let's say that, in fact, I take a function f of x, and I sample him at a bunch of evenly spaced points, which I'm going to draw very poorly, and the spacing between each of these is h. Right? By the way, I think in the course notes, I always say that this point is 0 and this point is 1. It doesn't really matter a whole lot. Anyway, so what I could do is I could say, well, my first one is going to be y0 equals f of 0, y1 equals f of h, y2 equals f of 2h, and so on, right? So I just took my function f of x and I sampled it at a bunch of points, yeah? And then we said, okay, well, what happens if we want to approximate the second derivative? Right? Well, we have that center difference formula, right, which says that y double prime at x is approximately what? y of x plus h plus y of x minus h minus 2y of x divided by by h squared. Yeah? So this thing is nothing more than a matrix that acts on these set of sample values yi, right? It puts like a weight minus 2, 1, 1, like that. Yeah? Very simple. And so what I did at the end of lecture, I know we moved a little bit quickly because I got nervous that I wasn't going to finish, I just stuck everything in the matrix here, and you can see it's got a very nice structure. Yep, this is a sparse matrix, and we'll see in a moment that in fact it's a sparse negative definite matrix, so life is very good. Yeah, and so, right, and so what we effectively just did was totally carried out the analogy that I suggested at the beginning of last lecture, right? That, again, that matrices are to vectors as derivatives are to functions. Yeah. In fact, this is a little bit of a weird analogy because there are other things that also act linearly on functions, but for our purposes, derivatives are enough. Another example would be integrals. Right. And there is such thing as an integral equation, just like a differential equation. It's considerably harder to solve. Okay. So finally, at the very end of lecture, I poked a hole in my own lecture. And said, okay, well we jumped, you know, when we talked about discretizing derivatives, we jumped to discretizing the second derivative of a function, right? And we said, well, we can write that as this matrix multiply, life is good, it's very slick, the matrix looks nice. And the question you guys should have asked, being the critical thinking people that you are is, well, why the heck did you choose the second derivative instead of the first? Yeah? And there are a couple choices for that. And actually the funny thing is, one of my colleagues who I've done a lot of research with and is now at Pixar, as you can see there's a lot of interchange between our lab and that place, sent me an email yesterday afternoon saying, with a screenshot of something he was working on, saying there's a bug and I can't figure it out, what the heck is it? And in fact, it is exactly this problem here. And so the problem is this. Let's say that I've sampled a function along a line. And in fact, some of you guys ran into this on homework 7 when you, remember you had to solve that little minimization problem where you approximate a function and you try to make it smoother? Yeah, and there were two terms in that minimization, right? One was that you match the value, and one was that you minimize the square of the derivative, yeah? And then people were asking, well, where do I put the square of the derivative? And that's an excellent question. My answer on homework 7 was, well, wherever the heck you want, I don't really care. But it is worth going back and being more careful about this. And if you code up your solution from homework 7, you might get results that you didn't predict. In particular, okay, so let's say that I have all these samples, y0, y1, y2, y3, all the way up to yn. By the way, there are n plus 1 samples. This is one of these things I screw up all the time. Right, and the question is, where do I put the first derivative of this thing? Yeah? When I took the second derivative, I had this nice sort of symmetric looking stencil. Oops, sorry, 1, -2, 1. Unfortunately, my research field, all the Laplacians are negative from where they are in any other research field, and it has destroyed my brain forever. But that aside, yeah, so the Laplacian stencil has this nice symmetric form, right, where the Laplacian sitting at this vertex takes stuff from the left and the right. Yeah? Well, what happens if I want to take the first derivative? Well, I have a lot of options, right? So let's say I want to approximate the first derivative at this vertex here. Well, I could put, you know, a 1 and a -1 there. It would be one option. I could put a 1 and a -1 there. Or I could put, you know, a 1 and a -1 there. Yeah? Obviously, you have to divide by different places. Each of these gives you a different derivative, and each has their own pluses and minuses, but you have to be very careful when you deal with these, because in particular, let's say that I chose this first option, where I take the value to my right and I subtract my current value. Yeah? Well then, what happens on the rightmost vertex? Well, I have to somehow make like a little ghost vertex over here, and use my boundary conditions to guess what this value should be. Right? Alternatively, if I look to the left, I'm going to have to do the same thing over here, and so on, right? So these two approximations where you look left or right are a little bizarre, because you're only going to look in one direction. You're going to need one boundary condition to guess your first derivative, right? So you might say, okay, well, Justin, this is a good indicator that in fact I should use the symmetric first derivative, right? I should put a 1 over here and a -1 over there. But this creates a really bizarre issue that isn't 100% obvious until you start playing with these operators, which is the derivative at y3 has no dependence on the value of y3. Do you see how this could be an issue? In particular, this derivative talks to these two guys, this derivative talks to these two guys, and so on, right? So in fact, what ends up happening is you'll couple the first, third, fifth, and seventh vertex, and you'll couple the you know second, fourth. Oh gosh, I counted wrong. But oh, you big. There you go. Like that. Embarrassing. But anyway, you'll couple the even and odd vertices, and in fact, they won't talk to each other at all. Yeah. So yeah, actually, my colleague, who shall remain nameless since he's a mathematician, you should notice this, got a result when he was solving an interpolation problem that looked like this. Right? Where this problem is zigzagging up and down very rapidly between every other slot as he's interpolating between this value and the right. But the particulars of his problem aren't all that important. Yeah? And immediately we're back to simulation. You have a, oh, shoot. Dear sir, you have a fence post problem, right? It's immediately clear that the bottom, the lower envelope and the upper envelope are just kind of two different functions and they're not communicating. Okay? And in fact, that's exactly what was going on. So having the symmetric derivative can actually be a very poor choice for a lot of these applications. So then the question remains, well, okay, so what the heck do I use? And the most common thing to do is to imitate the leapfrog scheme that we learned about for ODE integration. Right? So the idea here is I have all these samples, right? And let's say that I'm in yk and yk plus 1. Then what I'm going to do is think of the derivative as sitting at the midpoint of the edge. Right? And this actually resolves most of the problems that you have. So we're going to come back to this in a few minutes when we talk about fluid simulation. And you'll notice when we simulate fluids, it's very common to use something called a math grid, marker and cell. And the idea is that people that have designed these fluid algorithms are very careful to place like certain quantities on the vertices of a grid, certain quantities on the edges, or in their case, because it's in 2 dimensions, sometimes it'll be the interior of boxes. And it all has to do with how many derivatives you've taken. Because every time you take a derivative, you're kind of shifting from points to lines and so on. Cool. So anyway, that's why we skipped over the first derivatives, because the story isn't quite as clear. From a theoretical standpoint, that's because the first derivative is not an elliptic operator, but the second derivative is. Cool. So anyway, the big idea from this little part of our lecture, once again, if I've repeated myself enough times, is that you should, using SAT style notation. Actually, I'm told they don't do this on the SAT anymore. The derivatives are to functions as matrices are to vectors. And that is the coupling you should have in your head. Okay? And in fact, the sort of arrow that goes from one side of the analogy to the other is discretization. And if you have a discretization that doesn't carry out this analogy, I would be very suspicious. Yeah? There's like no reason why derivatives shouldn't be linear inside of this. Okay. So I thought I'd cover a couple sort of generic techniques for solving a linear PDE at least. And then we'll sketch 1 or 2 applications in a little bit more detail. Maybe we'll end early today, depending on time. But right, so if you recall, pardon me, our first sort of stab at all this was to define a elliptic partial differential equation. Right, our model 1 yet again is our favorite guy, Laplace's equation. In fact, we can write Poisson's equation by sticking a G on the right-hand side. And nothing too exciting changes. Right, and the question is, how can I solve this on a computer? Yeah? And actually, it's very straightforward, solving elliptic equations on at least to come up with sort of a reasonably accurate scheme. And basically, all you have to do is you say, okay, well now we have, right, you have our favorite, Justin's favorite analogy here, right? Derivatives are to functions as matrices are to vectors. You kind of wonder, like, say, the last lecture is never on the final exam. Anyway, right. So if you're trying to solve an elliptic PDE, how do you think I'm going to do it? Well, I'm just going to carry out this analogy and then do a linear solve. Yeah. So let's see what that means in a little bit more detail. In particular, so let's think of f as a function on 0, 1. Yet again. By the way, nothing interesting happens if you go to higher dimensions. This is just because notationally it's kind of a pain. But let's say our unknown is some function on the unit interval, and we're trying to find it. Right? Then what are we going to do? Well, we'll approximate f, right, with a bunch of samples yi. Right? And we'll just live on some line. y0, y1, y2, to y, again, n plus 1 samples. Well, okay, so that means that f now has become a vector y. And f is our unknown, right? But if I'm trying to solve Poisson's equation, which conveniently I erased, so let's write it again. Yeah? Let's do the same thing, so we're going to call this guy our discretization. By the way, you guys understand now when I say discretization, what I mean is that you take a function and you're sampling at a discrete set of points. Yeah. Similarly, I could take, so what is input and what is output here? The input is g and the output is f. Right? That's the equation I'm trying to solve. So let's say I discretize g. Well, then I can sample them at a bunch of points, and arbitrarily at 2 in the morning yesterday, I decided it should be b. So we're going to call our samples of this function g, we'll call them b, 0 all the way to bn. Yeah? Well, okay. So we just spent the last like 10, 15 minutes justifying what the second derivative operator should be. Remember, we have this little -2, 1, 1, -2, 1 matrix that I keep writing down? So if we want to approximate the second derivative of f, it's nothing more than that matrix, which I call L, times y. Yeah? And remember, I want to solve the Laplacian of f equals g, so all I got to do is put the vector b on the right-hand side. Yeah, every time we think that we're done with linear systems of equations in CS205A, they come back for another reprise. Yeah? So if I want to solve an elliptic PDE, all I have to do is solve this linear system of equations. Yeah? And the nice thing about the matrices, at least for linear PDE, by the way, if it's nonlinear, then chances are this will be a nonlinear system of equations to solve. Yeah? But anyway, this matrix L has a lot of nice properties. And we'll prove them all in a second, but it should be kind of obvious that it should have some nice properties. In particular, L is a derivative matrix, right? Even, yeah, so I wrote down kind of a stupid problem here, right? This is, you know, the second derivative of f equals g is a pretty easy problem to just solve by hand. But even if this is in higher dimensions or something, since L is a derivative, what it means is that each point under L is only likely to talk to his neighbors. Right? So even if I have a ton of samples, my matrix, the number of non-zero values in this matrix L is going to scale sort of with the number of samples rather than the number of samples squared. It's a very nice property. And in fact, so our system is already sparse, right? And remember we spent quite a lot of time botching the derivation of the conjugate gradients algorithm, which is all about sparse positive definite matrices. And in fact, I spent all this time telling you that elliptic equations you should think about as sort of the positive definite of the PDE world. And in fact, that analogy carries out conveniently on this slide. So if you want to solve an elliptic PDE, what you should keep in the back of your head is that in fact, all you're doing is inverting a positive definite matrix. And so for this kind of running example that we have so far, by the way, sometimes I'll say positive definite and mean negative definite. What really matters is definite, yeah. If you want to solve ax equals b and a is negative definite, you do have to be a little careful in conjugate gradients to solve negative a equals negative b, negative ax equals negative b, yeah? Because then it's positive. Anyway, right. So the question, remember we had this Laplacian matrix, or in our case just a second derivative matrix, which is very easy to write down, right? This guy here. Yeah. So remember we used Dirichlet conditions, meaning that I fixed the left and right endpoints to have value 0. Then, well, how can we prove that this matrix is positive definite? Well, we have about 25, or negative definite, in fact. We have about 25 different ways, but there's actually a very slick proof that I like a lot. And being a math guy, I have to give you the slick proof. Anyway, so the observation that you should make is that, what is the second derivative of the function? Well, so if we use this kind of silly notation that I've introduced in our last lecture, right? We think of df dx as kind of multiplying f and this operator d over dx. So let's say that I carry that out. Well, so remember that we have that is the Laplacian at least in one dimension. Yeah, but you can think of this as d over dx dot d over dx. In fact, obviously this notation kind of carries out. And this gives you some indicator, this is a very fuzzy argument, that your matrix should be positive definite, because you have a square sitting in here. Yeah? This is very fuzzy. But, here's the nice thing, is you can use your fuzzy intuition to intuit a rigorous proof on the discrete side. And in fact, this is what I did late last night while I was making this lecture. I said, well, okay, I want to prove that L is positive definite. I started by just computing what x transpose Lx is, right, and trying to prove that this number is positive. But it turns out that's kind of a hairy proof. And I thought about it for a little bit and said, well, okay, so I should be able to get to the second derivative by taking the first derivative twice. Yeah? And in fact, one thing you can do is say, well, what's the simplest first derivative? Well, you just keep putting 1s and minus 1s on adjacent vertices, just like we've been talking about. And I can construct a matrix that does that. And in fact, it turns out that your Laplacian is nothing more than, you have to be careful, there's a negative sign here, but minus that matrix transpose times itself. Yeah? By the way, this matrix has n plus 1 rows and n columns. This is how I got around that weird boundary condition issue I was talking about. I just added something inside. Anyway, so you can, I got this proof by playing in MATLAB, and I recommend you guys do similar things. Right, so if L, by the way, a little bit of review here. If L is equal to minus D transpose D, let's prove to ourselves that this matrix is indeed positive, negative definite. Yeah? So how would I do that? Well, now if I take a vector x and I compute x transpose LS, right, we now know that that's the same as negative x transpose dx, right? That's a d. And, or the same proof that we've basically written down 3,000 times in this class in different forms says this is the same thing as minus the norm of dx, the 2 norm squared. Yeah? And obviously norms are positive, I've got a negative there, so this is less than or equal to 0. And if you look at the structure of this matrix here, it's easy to check that the only time d can be 0 is exactly when x is 0. Right, because it's subtracting adjacent pairs. Cool. So anyway, I just totally carried out all of our favorite analogies from linear algebra to PDE, right? What did we do? We started with an elliptic equation, right, which was the derivative times function equals other function. We discretized that, and lucky for us, it became matrix times vector equals vector. And in fact, since our PDE was elliptic, the matrix that we wrote down ended up being definite. Yeah? This is great news, because what can I use to solve elliptic PDE? Well, all of our favorite algorithms from a couple weeks ago, week 7-ish, right? Because conjugate gradient actually was originally designed for systems like this, right? They are large, sparse, and positive definite. Yeah? In fact, your textbook, Heath, actually puts the discussion of conjugate gradient in the chapter on PDE. Now, since we motivated conjugate gradient using least squares and some machine learning problems that didn't make any sense anymore, but it's a very common viewpoint in numerical analysis that conjugate gradient is the algorithm for PDE. In fact, usually it's what we use, at least out of the box. Right, that's a quick review. I suppose I already given away one answer to this, but let's say that I'd like to solve an elliptic PDE. You guys need to name for me. Okay, so one way to solve this would be to use conjugate gradients. The other one would be what? If this is a smaller system of equations. We only covered 2 things in this class that have to do with positive definite matrices. Cholesky factorization. Yeah. And so those are the 2 primary tools for solving associative equations. I recommend you guys review this stuff. Right. So that's basically the story for elliptic PDE. You discretize everything, you get a linear system, and then you solve. Yeah? Things can become a little bit funky, right? Like, what we didn't cover is, for example, if we discretize a function that's not on a nice, like, axis-aligned grid, like what I've drawn for you here, then there's a little bit of work to understand what it means to have a second derivative on an irregular domain like this, right? The typical approach is to stuff in full of triangles and put values with the nodes. But if we had one more lecture in this class, I would go over that. But such is life. Anyway, so our model equation for elliptic didn't really have any time dependence, right? It was all about interpolation. But then our other 2 model equations, the heat equation and the wave equation, had this new variable t for time. And so methods for solving elliptic or rather parabolic and hyperbolic equations, right? These things with time dependence usually, are sort of acknowledge that fact especially and treat that time variable often a little bit differently from the others. Cool? So let's say that I have a time dependence